The last thing we want to look at in Chapter 12 is bond polarity and molecular polarity. When we started talking about bonds, we saw that some bonds that are formed are polar covalent, meaning that they create a partial negative and partial positive charge because the electrons spend more time around the more electronegative element and less time around the less electronegative element. So let's think of a molecule such as HF. HF has a charge distribution where the fluorine would be partially negative and the hydrogen would be partially positive. So the molecule as a whole, draw it in over here, has a negative side and a positive side. A negative side to the molecule, a positive side to the molecule. Partially negative and partially positive, but we do see a charge distribution here. We get the dipole moment. We can draw an arrow that points from the positive side towards the negative side. Here to draw this in here. You can see here on water down at the bottom, water has two hydrogen-oxygen bonds. Oxygen is more electronegative than hydrogen, so oxygen gets two delta minuses. Each hydrogen gets a delta plus. So we have a positive side and a negative side to this molecule. So we can draw our arrow showing the dipole that's created. These are known as polar molecules. Now let's take some more examples. When we have HCl, we form polar covalent bond. We want to show that this one side is more negative than the other. So you get the negative side, the positive side. Based on the shape, we know that this is linear. So based on the fact that it is linear and it has a positive and negative side to the molecule, positive side, negative side, we would have what's known as a polar molecule. It has polar covalent bonds. It is a polar molecule. Just because you have polar covalent bonds doesn't mean it has to be a polar molecule. It means it could possibly be based on the shape and the structure. Another example, CO2. Now in CO2, we get a dot structure that looks like this. Oxygen's more electronegative in each bond, so the oxygens get the negatives. The carbon gets the positive of each bond. If you look at this, you have a negative side. So you have a negative side with positive center. In this case, we have polar bonds, but the molecule is non-polar. Typically, if we have a linear molecule with more than two atoms, they're generally going to be non-polar. Let's look at BF3. This is a trigonal planar. Once again, polar bonds, non-polar molecule. You've got your F, 3 fluorines. The negatives are around the outside. Fluorine would get each of the partially negatives. Boron would get the positives of each bond. So it's got a positive center, negatives around the outside. It is non-polar. Finally, let's look at water. Water is an angular shape. It has polar bonds and is a polar molecule. If you draw the shape correctly, you see the negatives are up here, the positives are down below, so we have a positive side and a negative side. It is very important that you know the shape to understand whether something is polar or non-polar molecule. So let's look at how water actually dissolves a number of things based on this property. If you have it near ions, the positive side of water can be attracted to the negative ions, anions, and the negative side of water can be attracted to the cations. And this is how we get the ionic dissociation that happens in ionic solutions. So let's look at some examples. NF3. We draw out its dot structure. It's trigonal pyramidal. So it actually has a shape like this. So we get our negatives down here and our positives up top. So this is polar. O2. This has nonpolar or pure covalent bond. It doesn't even have a polar covalent bond. So there is nothing positive and negative in the molecule, partially, so that we have definitely a nonpolar molecule. HCN. This is linear. We said most of the time linear molecules are of more than 2 atoms are nonpolar, but in this case, let's look at our electronegativities. Carbon is more electronegative than hydrogen. Nitrogen is more electronegative. Sorry, this should have been a negative and a positive. Nitrogen is more electronegative than carbon. So we have a negative side and a positive side. This would be polar. CH3F. You think of the structure. This is tetrahedral. Carbon is more electronegative than hydrogen. But fluorine is more electronegative than carbon. So we have a negative side and a positive side. This is polar. A couple more examples. H2S. This is angular. We have a negative, positives. This is polar. CH4, tetrahedral. Everything around the outside would be positive, the middle would be negative. This would be nonpolar. And SO3. Remember, this is the one, those molecules that has resonance. It ends up being trigonal planar. So these are all in the same plane. Oxygen would get the negative, sulfur would get the positive. This is non-polar. And SiO2, this is the same structure as CO2, Si and C being in the same family. This would also be non-polar. So to determine polarity, you must draw the shape, draw out the Lewis structure, determine the shape, and then from that you can determine whether it has a positive side to the molecule and a negative side to the molecule, which would make it polar, or if it does not, then it would be non-polar.